Welcome to the course on power electronics with wide bandgap devices. This is the first lecture. In this lecture, I am going to discuss about different types of wide bandgap devices. This is introductory class. We will try to understand that how these devices are different from the silicon devices. As you can see in the first slide, so here I have given one graph where it is showing the increasing energy with respect to the bandgap. So the first question in this particular course should come to your mind, what is bandgap? So bandgap is basically difference or the distance between valence band and conduction band. Now it can come to your mind, or you already know about valence band and conduction band. So valence band is the band where electrons are occupied at highest level. Means maximum number of electrons are occupied in valence band. So if the material is insulator, so then what happens? Then the band gap will be more. That means all the electrons will be occupied in the valence band and there will be none in the conduction band. So in order to make this particular material to conduct, we have to provide highest value of excitation. So as you can see in the semiconductor, so semiconductor is what? So it is also one type of material which is having less band gap as compared to the insulator. So as you can see here, the difference of insulator band gap and the semiconductor band gap. So in this particular semiconductor, you can see here, so this particular, so probably you can see the circle. So here the band gap is less. So that means what? So if we can provide external excitation, so then this semiconductor will be conducting. Now the third material you can see here, metal. So here in this case you can see the valence band and the conduction band, it is overlapping. That means what? So it doesn't need any external excitation to make the material conducting, or to bring it to conduction mode, we don't have to provide any external excitation. Now we will be dealing with this semiconductor. So semiconductor, as you can see here, there is some band gap, and this band gap is also not constant. Means with respect to different material, this band gap is also variable. Means in insulator, it will not conduct as the band gap is very high. In metal, it will be always in conducting state. In case of semiconductor, we can make it conduct by providing some external excitation. So you can see here, so that these definitions I have written in the right hand side. So basically, if we can provide some energy which can actually allow the electrons to move from valence band to conduction band, then the material will come to conduction state. So now in this particular lecture, we will be dealing with semiconductors. So mainly I will be discussing about silicon, silicon carbide and gallium nitride. So some of you probably have heard about this silicon carbide and gallium nitride, and they are known as wide bandgap devices. You can see in this particular graph, so I have provided here one graph where the comparison between silicon, silicon carbide and GaN are given. So you can see here with respect to the energy gap. So energy gap, it is actually shown here, the silicon carbide and GaN, they are very close to each other. And below this particular graph, I have also given this actual value of this band gap. In case of GaN, you can see the band gap is 3.5 eV. And in case of silicon carbide, 3.26 eV. They are quite close to each other. Now in case of silicon, it is 1.12 eV. So which is much less than silicon carbide and GaN. That is why this devices, silicon carbide and GaN, are known as wide bandgap devices due to higher value of the bandgap. Now you can see in this particular graph there are different factors given along with the energy gap. So one factor is electric breakdown field. So you can see as the band gap is higher, the breakdown field is also higher in case of silicon carbide and GaN. And in case of thermal conductivity, you can see, so thermal conductivity, it is also higher than that of the silicon. And same in case of electron mobility and saturated electron velocity, they are also higher than that of the silicon. So what is the need of these devices? Why we need to consider these wide bandgap devices, or what are the advantages we may get? So in the left hand side you can see this material property comparison is given between silicon and silicon carbide. So you can see here the breakdown field for silicon is given as 0.3, and where the silicon carbide can have 2.8. So basically silicon carbide is going to have higher voltage capability and it will be much thinner that of the silicon device. So you can see here the silicon structure, silicon MOSFET structure is compared with silicon carbide MOSFET structure. So where the silicon carbide structure, it is actually given 1/10 of that of the silicon structure. Means for the same rating, the size of the device will be much lower, and also it will have lower resistance. So the losses will also be much lower, and the voltage breakdown capability for silicon carbide will have much higher than that of the silicon for the comparable size. So this is the main motivation to look for this kind of wide bandgap devices. So basically the focus is to move towards high power density system. High power density means the size will be much smaller as compared to the existing solution. So in that process we should not lose the efficiency and cost also should not increase. So for the same system we are trying to achieve much lower size, higher efficiency and low cost. Because silicon materials, it has some capability which cannot go beyond that. That is why people started looking for other materials. Then they found these wide bandgap devices, they are better in properties as compared to silicon. So what ways they are better and how it is going to become advantageous for power electronics application, so that we are going to see in this particular course. So these are some applications where basically wide bandgap devices are kind of can be used, and it is actually kind of projected that in future most of the power electronics applications will be replaced by wide bandgap semiconductors rather than silicon devices. So you can see here, so silicon, it is now kept at the beginning level. So basically in terms of power level and the voltage level, it is shown here the application where the silicon will be limited, that will be for comparatively low power and low voltage level. Although you are probably familiar with that silicon devices are available for high voltage. So the problem is that once we try to go for high power level, the size of the system and efficiency, those reduces. So we have to select an optimum point where the size, efficiency, cost, everything will be optimized. By considering those factors, in this particular graph, it is shown that silicon will be limited for low power, low voltage level, and for higher voltage than that of the 80 volts till 650 volts, the applications mainly will be focusing using GAN devices. So the applications you can see here, some of the applications are given where basically GAN will be suitable or can be applicable, mainly this laptop adapter, PCs, then home appliances, then solar microinverter, motor drives, residential EV charging, e-mobility, and then hybrid vehicles. So those are the some of the applications which are shown here where GAN will be more applicable than that of the silicon or silicon carbide. And there is a overlapping period, here it is shown here, overlapping region where both GAN and silicon carbide will be suitable. So what are those applications? So the voltage level will be from 650 to 1200 volts. So where the applications will be focusing mainly data center UPS, then residential solar, then electric vehicles. So where any of the devices, either GAN or silicon carbide, can be used, but it is advisable to not use silicon as it may have higher size and lower efficiency. So that is why this silicon in those applications can be replaced with GAN or silicon carbide. Now beyond 1200 volts, you can see here beyond 1200 volts, so the application will be focusing mainly with silicon carbide devices. So the silicon carbide devices are basically capable of having higher voltage capability. The breakdown voltage will be here shown, it is shown maximum it can be till now what is available is 6.5 kV. So where exactly those devices will be applicable? So you can see here one of the applications is rail power. So traction application, EVs, high voltage EVs. So EVs can be different types, two-wheeler, three-wheeler, then four-wheeler, then heavy electric vehicles. So there are also different voltage level in EVs. So some EVs they are considering 48, some are considering 400 volts. Now in near future people are focusing on high voltage EVs, means the voltage level will be 800 volts, voltage level of the battery. So there these silicon carbide devices will be suitable. Then the commercial EV charging, industrial robotics, industrial drives, medical imaging, then wind power. So all these places silicon carbide will be more suitable than that of the GAN or silicon devices. So these are the some of the applications. So it is expected to use these wide bandgap devices, or these devices will have much more advantage as compared to silicon for these applications. Now with respect to this frequency and the power level, if we try to see, then you can see here. So the gray one is shown here is for silicon. So silicon, as so most of you already know, as we try to go for higher frequency level, then the power level will be limited. Means it cannot happen that we can have both high power and high frequency. So in case of silicon, so if we try to go for higher frequency, let's say 100 kilohertz in that level, then the power level will be limited. It will be less than 1 kilowatt. Now if we try to achieve high power, let's say 100 kilowatts or more than that, then the frequency will be limited. It can be maximum of 1 kilohertz or 10 kilohertz. So you can see from this particular graph. So output power versus frequency. Now where exactly GAN and silicon carbide stands? So GAN, you can see the pink color graph here shown. So here GAN will be suitable for very high frequency application. Very high frequency means it can go to gigahertz level. So here it is shown 1 megahertz and it is like near to 10 megahertz. So there the obviously the power level will be limited. Now if we try to operate the power electronics converter at high power level, so the GAN is capable of operating, here you can see in this graph, it can go till let's say 10 kilowatt. So there the frequency, here the 10 kilowatt, there the frequency will be limited. Frequency then it will be maximum of 1 megahertz or less than that. So that is where the limitation comes for GAN. So GAN will be more suitable for very high frequency applications or the medium power and high frequency applications. So here we are considering 1 megahertz as high frequency. Now where exactly silicon carbide stands? So you can see this orange graph. So where the silicon carbide, it is shown, it will be more suitable for very high power level. Very high power level means the power level you can see here, it can go maximum to 10 megawatts. Now if it is operating at that power level, then obviously the frequency will be limited. So in that time the frequency will be some few tens of kilohertz. But this device is suitable to operate at around let's say 500 or 600 kilohertz. So there the power level will be limited to let's say 100 kilowatts. Silicon carbide devices are more suitable for very high power applications. So medium frequency and high power. So GAN is suitable for medium power and high frequency, and silicon carbide devices are suitable for high power and medium frequency, where the silicon operation is limited to comparatively low power and low frequency applications. So the part where the silicon carbide is limited, so it is shown here, so below 10 kilohertz, below 100 kilohertz and 100 kilowatts power level. So there we can get optimum operation by using silicon devices. So this is what is given here in this particular slide. So you can see here, so the trend, so market of this wide bandgap devices, so where exactly we are focusing. So basically right now we are focusing to replace the silicon devices with wide bandgap devices. Now this wide bandgap devices are basically gallium nitride and silicon carbide. They are available commercially. There are other wide bandgap devices also like diamond, which is still in research level. It is not yet available commercially. That is why for power electronics application it is very difficult to find out what can be advantages using those devices or what can be challenges we can see by using those devices. So that is why this course is limited for gallium nitride and silicon carbide type of wide bandgap devices. So now this current trend, so you can see here in industries and then different applications like whatever you can see around you, like electric vehicles, renewable energy, consumable electronics. So there the current trend is to replace the silicon with wide bandgap devices. Now in future it is estimated that silicon carbide and GAN power technologies, it will exceed $20 billion annually by 2026. This is what is given here in this graph. So it is shown here that with respect to GAN opportunity. So right now it is shown that in 2022 what is the condition, and in 2026 what will be the situation. So GAN market will increase from 1% to 16%. And the right one for silicon carbide you can see here. So right now the usage of these devices for different applications, it is around 14%, and it is expected to increase 46% by 2026. The schematic representation of this silicon carbide and GAN, it is shown in this particular slide. So right now I'll just show you this structure. Details I'll be discussing in next class. So you can see here, so there are different types of structure given. One is silicon carbide vertical planar gate depletion MOSFET. another is silicon carbide vertical double trench MOSFET, another is silicon carbide vertical cascade JFET. So you can see here, so the current flow direction for silicon carbide, so the drain is at the bottom layer and from bottom layer it is going towards upside. Now this structure is quite similar to the silicon structure which you already know. Now in case of GaN, the structure is completely different. You can see here this GaN P GaN gate HEMT and then GaN cascade HEMT. So this P GaN structure, it is, you can see there are actually drain, source, and then horizontally it is having current flow from drain to source. And this structure you can see here, this P GaN, L GaN and the GaN layers are formed here in this particular way. And if it is cascade kind of structure, so there will be one low voltage silicon device connected on top of this particular device. So where basically the gate is placed in case of P GaN structure, there the low voltage silicon structure is present. Why is so? I will show you in the next slide. So basically this is the simplified structure of GaN. So I am not discussing in details about silicon carbide structure because the operation is similar to that of the silicon. But in case of GaN, what happened? So basically GaN, how the current conducts in the reverse direction, so that is quite interesting. So you can see here when drain to source voltage is applied, so basically the two-dimensional electron gas layer is formed between L GaN and GaN layer. So that is because piezoelectric polarization, and through this layer current will flow. So you can see in the right one, so when positive voltage is applied to the gate, so then drain to source current is flowing through this two-dimensional electron gas layer. And this two-dimensional electron gas layer is actually very new kind of concept in any semiconductor material or as compared to silicon material, silicon device. So you can see here, so when the zero voltage is applied, so that time the device will be still in conduction state. So this is depletion type of device. So that is why we have to provide negative voltage in order to completely turn off the device, because this two-dimensional electron gas layer is already formed. So the current path already exists. So if we don't provide negative voltage, so then it will be normally on type of device. And in order to use this particular device for power electronics converter, that will be a challenging task because the device is already in on condition. And if we don't turn off, so then there will be mal-operation. So that is the reason this GaN device needs negative gate voltage in order to completely turn off. So this is for P-GaN HMT structure. Now you can see here, this is how the GaN MOSFET looks like. So there are different layers which are actually placed, and this is SMD kind of device. And in this particular device which is shown here, so GS66508B, so it is bottom cool kind of device, means so the PCB where the device will be placing, so there only you have to provide heatsink if it is required, otherwise you cannot connect the heatsink on top of the device. So that's why bit challenging to connect heatsink, and special kind of requirement of heatsink or the knowledge of heatsink connection is required. And this is the structure of silicon carbide MOSFET. This is how it looks like. It is similar to that of the silicon device. It is having different drain, source, gate, and you can see here this is the symbol of the silicon carbide MOSFET. This is the comparison of the GaN device with respect to MOSFET. So you can see here the GaN device is shown in the right hand side, in the left hand side it is MOSFET. So the reverse current flow path for GaN is very interesting because it doesn't have reverse diode connected to it. In case of MOSFET, you can see there is a reverse diode which generally forms in any device, in silicon, silicon carbide, any device, it will have reverse diode which will be formed in the device and which will allow current to flow in the reverse direction. Now this is also known as parasitic body diode of the MOSFET, and then due to this there can be possibility of DVDT failure, and also due to this reverse recovery problem may arise, and this is not actually ideal kind of device for half bridge hard switching operation. Now come to that GAN switch. So GAN switch is having structure which doesn't have any anti-parallel diode, anti-parallel body diode. So does that mean that there will be no reverse current flow? There will be reverse current flow. So how it flows? So the flow will be from source to drain. How this current flow will be? That will be through the two-dimensional electron gas layer. You can see here, due to the absence of this body diode, so basically this device is having high DVDT ruggedness, and as the diode is not present, so there will be no time required for reverse recovery. So there will be zero reverse recovery time or loss. And this device is suitable or ideal for half bridge hard switch or soft switch operation. So basically, as compared to silicon and silicon carbide, GAN has different structure and also symbol is different. It doesn't have body diode. That is actually advantageous because there will not be any reverse recovery problem. So is that the only thing? Also there will be a disadvantage. Due to the absence of this reverse diode, so this reverse current flow can cause high voltage drop. Means the losses during the reverse operation will be much higher than that of the silicon or silicon carbide device in case of GAN device. So you can see here the symbol of GAN. So the left one is the E-GAN configuration, and then right one is the D-GAN configuration, so which is also known as cascade depletion mode device. So the left one is enhancement mode device or E-GAN device. It is normally off, turn on with a positive gate voltage, and the cascaded depletion mode device, it is normally on and requires a negative voltage to turn off. And this device, you can see here, the structure is basically, it is having one GAN device which is actually connected to one silicon MOSFET. So the gate where it is connected, so gate will be the silicon MOSFET gate, and which will help the GAN device to turn on. So this is the difference between E-GAN and D-GAN configuration. So let's see the data sheet of these devices. So how these devices are different from each other, that we can see from the data sheet. So this data sheet is for the GAN transistor, which is having rating of 650 volts, and this is bottom side cool device, as you can see here from this device structure. So the top side it is written GAN and then GS66504B, the part number of the device, and the bottom side it is having different points. So basically access point of the drain, gate, source, all will be placed in the bottom side, and this is SMD type of device. And then this kind of the requirement of SMD type of device for GAN is due to the arise of low inductance in the package. So whatever you have seen for silicon carbide or silicon, that can cause arise of high inductance, and that can cause problem for high frequency operation. That is why these kind of devices are having package which is SMD in nature and much thinner than that of the silicon or silicon carbide device. So you can see here, so this gate drive requirement is 0 to 6 volts, and then transistor can tolerate minus 20 to plus 10 volts. Means if we by accidentally if we provide minus 20 volts or plus 10 volts, still the transistor will be able to survive, and it is suitable to operate very high switching frequency. Very high means it is even suitable for operation more than 10 megahertz. Then this is fast and controllable fall and rise types, and reverse current capability. It is suitable for reverse current flow operation, and it is having zero reverse recovery loss. And the size of the PCB footprint, it is very small. You can see here, this is 5 multiplied by 6.6 millimeters square. So it is this small. So now you can see the operation of this device is suitable for a junction temperature minus 55 to plus 150 degree Celsius. So this device can be used in places where the temperature can go in negative side minus 55 degree Celsius and positive side plus 150 degree Celsius. And storage temperature is also same, and drain to source voltage, as I have already told you, 650 volts. Now this drain to source voltage during transient condition can also be 750 volts. If there is any spike or anything which is of 750 volts, still the device can survive. The gate to source voltage, it is given that minus 10 to plus 7 volts. So you can provide any voltage in between. So it can be, let's say, minus 5 to plus 6. So in that level. So during transient condition, the device will be able to take minus 20 to plus 10 volts. The continuous drain current rating in this device is 15 ampere at 25 degrees Celsius. If the temperature rises to 100 degrees Celsius, then the continuous drain current will be lower, which will be around 12.5 amperes. And if there is any pulse current or the transient current which is of 30 ampere, then the device will be able to operate. Now you can see in the right hand side electrical characteristics for this device is given. So here important thing to notice is that drain to source on resistance. So drain to source on resistance for this particular device is 0.258 ohm or 258 milliohm. So you can understand from this that conduction loss will be lower. Now the threshold voltage, which is very important for this particular device. You can see here minimum is 1.1 volts and typically it is 1.7 and maximum is 2.6 volts. Means what? If we provide any gate voltage which is from, let's say, 0 to 6 volts. So if there is any transient of 1 volt comes during the off time in the gate, then that will cause the device to false turn on. That is the reason it is always advisable to provide negative voltage. Then at least there will be some gap between the threshold voltage and the gate voltage. But if there is no gap, so there can be problem of false turn on. So that is one of the main problem of this kind of devices. The threshold voltage is very low. Now get to source current, it is given IGS, it is 80 microampere. And drain to source leakage current, it is given, typically it is around 1 microampere. So the losses will be less. Drain to source leakage current, it is 200 microampere. Now internal gate resistance, you can see here 1.4 ohm. It is given 1.4 ohm. So now the main thing for this device operation at high frequency, the capacitances, different parasitic capacitances, input, output and reverse transfer capacitance. You can see here this reverse transfer capacitance is around 1 picofarad, output capacitance 31 picofarad and input capacitance 120 picofarad. The very low value of these parasitic capacitances allow the device to operate at high frequency. Because the gate charge requirement gate charge requirement is very low in this particular device. So this is the reason the device is suitable to operate at very high frequency. Now let's see the datasheet of silicon carbide and where exactly it is different from the GaN. So you can see here this device is also shown for same voltage level. This is 650 volts and RDS on here it is 30 milliohm. So you can see here this conduction loss is much lower and the drain current capability is 70 ampere. So in this case you can see here different other factors. So basically drain to source voltage 650 volts, continuous drain current is 70 ampere for 25 degrees Celsius and it can reduce to 49 ampere if the temperature increased to 100 degrees Celsius. Now pulse drain current capability for this particular device is 175 amperes. That is very high. And gate to source voltage, it is advisable to give -4 to +22 volts, anything in between that. So basically the voltage level generally suggested for this particular device is 0 to +18 volts. Means it can also be given 0 to +15 volts, which is of similar level of silicon device. Now you can see here different capacitances for this device. So this input capacitance, output capacitance and reverse capacitance. So you can see here the input capacitance for this device is 1526 picofarad, output capacitance is 89 picofarad and reverse capacitance is 42 picofarad. This is much higher than that of the GaN device. That is the reason silicon carbide device operation will be less than that of the GaN device operation in terms of frequency level. So GaN can operate at much higher frequency than that of the silicon device due to presence of lower value of these different parasitic capacitances. And accordingly the gate charge level of the silicon device is also will be different. So these are the different rise time and fall time for the silicon carbide device. And this is the symbol of the silicon carbide device, you can see here. So basically 1 and 4, these 2 points are given for gate and drain, and then 2 and 3 are for source. Now let's see the silicon MOSFET. So the silicon MOSFET, the voltage level is slightly lower than that of the GaN and silicon carbide, which is 500 volts. Here the RDS on is 0.27. So you can see here this is much higher than that of the silicon carbide device. And the structure of this silicon device, you can see here gate, drain and source, and this is basically schematic representation of the silicon MOSFET, which is similar to that of the silicon carbide. You can see here, so the drain to source voltage is 500 volts and gate source voltage it can be plus minus 20 volts, and it has continuous drain current capability 20 ampere at 25 degrees Celsius and 13 ampere for 100 degrees Celsius. Now other points you can just go through. So the important thing here I'll just show to you is the parasitic capacitances. So the parasitic capacitances here you can see input capacitance of the silicon device is 4200 picofarad, output capacitance is 870 picofarad and reverse transfer capacitance is 350 picofarad, which is higher than silicon carbide and much higher than that of the GaN device. This is the reason the operation of the silicon is limited to comparatively lower frequency level. And also there are like delay time and rise time for this silicon device is given here. So this is just to show you the difference of different capacitances and what is the reason so that the devices can operate at high frequency. And there are other points which are also available in the datasheet that you can just go through, and eventually we'll look into it different parts for different types of discussion. So for driver designing part, I'll be showing different part from the data sheet. So that we will see later. So now the advantages. What are the advantages of silicon carbide and the CAN devices? So first thing is the loss reduction. So you can see here, as the capacitances are much lesser than that of the silicon device. So GaN is having much lesser capacitance than that of the silicon carbide, and which is having lesser capacitance than of the silicon. So then the gate charge, drain charge, or it is requirement of those charges are much less. So then rise time and fall time will be much lesser. So it is much less in case of GaN as compared to silicon carbide as compared to silicon. So then what will happen? The switching losses will be much lower. So switching losses in case of GaN will be lower than that of the silicon carbide, which is also having lower switching losses than that of the silicon. So the efficiency will increase in these devices. So we can operate at much higher frequency, which will reduce the size, and the efficiency also will be higher. The second point is the elevated power density. As you know, as these devices allow us to operate at higher frequency, so then what happens? Then the size of the overall system will reduce down. Size of the passive component will reduce down. And if the losses are less, so the heat sink requirement will also be less. The details of this heat sink and the thermal modeling will be seen later in this course. So basically the size will be much more compact, and it will have better thermal characteristics, which will lead to smaller, lighter systems. Now, third point is the extended operational range. So now these devices are suitable to operate at high voltages, and also which will be suitable to operate at high temperature as compared to silicon devices. Means if the temperature increases, the failure of the devices will be much lower as compared to silicon device. So the reliability of the overall system will increase. So as you have seen, one property, as the temperature increases, current level reduces. Similarly, different other parameter in the device, it will increase. So that will cause more losses to occur, and that will again cause more heat generation, and temperature again will increase. And this will cause failure of the system. If the device's properties doesn't change much with the increase of the temperature, then what will happen? The system will be able to operate at higher temperature level, and then reliability of the system will also increase. And the fourth point is that enhanced switching dynamics. Then this faster switching will allow precise control, reduce distortion, and improve the performance. So basically the dynamic performance will be better than that of the silicon. Steady state performance will remain same, but due to the less switching time, it will have less time when this oscillation will be there or the distortion will be there. So then the dynamic of the overall system will improve. Now you know about the advantages. Obviously these devices are having better properties than that of the silicon, and it is expected to achieve better system by using these devices. But this doesn't come without a cost. There are challenges, and this will give us the window for research in this particular area. So what are the challenges? First is the cost and availability, because these devices are new and not many manufacturers are available for these devices. So accessibility of these devices are also not as easy as silicon devices, and also they are much costlier than that of the silicon device. So that is the first challenge. So basically first is the very high cost, and also it is not easily available. You have to spend a lot of money to get these devices for your work. or for any application. Now second thing is that integration with existing system. So basically these devices are new, so it is having new design. So these devices cannot be integrated directly with the existing system. Let's say for GAN. GAN has different gate drive requirement. So then currently the driver whatever available for silicon devices we cannot directly use for GAN application. So it cannot be directly integrated to the existing system. So this is another challenge. Third is that these devices requires continuous research and development to not only to reduce the cost and also to find out other properties. In datasheet you may or may not find all the properties as the silicon device. So silicon device datasheet if you open you will find much more information than that of the silicon carbide or GAN. So some information still unknown. So in order to know this information, continuous research in this particular area is required so that we can have all the information. That is one opportunity. Also like that comes in the way for application. So still unknown factors are there for which in any application those devices cannot be directly used. And the fourth one is the environmental and social impact. So now we know that these devices can give us better efficiency and reduce energy consumption. So these are for environmental reason it is very good and it has like positive social impact also. But still we are not sure until and unless we completely use it in any application. And also there are another important thing is that in industry the unavailability of the manpower who are kind of trained using these devices. So the people who are working in industry they are using silicon for long time, so they know about the device, the system with those device, how it will behave. But in case of GAN and silicon carbide the knowledge is not there much for the industry people. So that is why in order to use it completely this knowledge is required. So this is one of the main challenges for the development of the silicon carbide and GAN based systems. Let's hope in future probably more number people will have knowledge of these devices, so it will help industry to accept these devices or technology based on these devices, which will eventually help to reduce the cost and it will increase the availability, and also other factors will also become kind of positive with respect to these devices. Thank you. This is all for today's lecture. More on these devices I will be discussing in the next class.